Now, continuing on the theme of client-side technologies that are useful in a cloud environment, let's discuss Spring Cloud Hystrix and the circuit breaker pattern. By the time we're done with this module, you will be able to understand how software circuit breakers protect against what we call cascade failure. And you'll see how to use Spring Cloud Netflix Hystrix annotations within your software to implement circuit breakers. We'll also learn how to establish simple monitoring of circuit breakers using Hystrix, Dashboard, and Turbine. So first, let me begin by exploring a scenario known as cascade failure. And I'll show you how the circuit breaker pattern can resolve this. And then I'll jump in and I'll show you Spring Cloud Netflix Hystrix and demonstrate how we can easily add the circuit breakers to your system. So first, let's explore something known as cascade failure. Whenever you have a large number of interacting services, there is always a possibility that one of them could be in a failed state for any number of reasons. In fact, if you have 600 microservices, such as the Netflix example mentioned earlier, I think you can depend on at least one to be in a failed state a good portion of the time. The issue is the effect that the individual failures have on the other services. Take a look at this illustration. You can see that I have a single failed service in the bottom here, the one that's in red. And you can see its effect on all of the other clients. And then their clients are in turn affected, and so forth and so on. And the result of this is a ripple effect throughout our cluster of services, inevitably leading to visible problems in our user-facing interfaces. A microservice architecture is very vulnerable to this type of cascade failure, and if we're not proactive in addressing this, we can count on a lot of trouble. Now, to be fair, a monolithic application can have a failure of a single component cause a ripple effect across the application, but we are far more vulnerable to this in a distributed system. Recall the thing I mentioned earlier about the fallacies of distributed computing. In addition to our software failing, we could have a slow network, a node could drop out and be unreachable, a security policy could change, and we could suddenly not be able to reach a node, and so on. Another way to look at this is to think about a typical infrastructure service level agreement, like the one offered by Amazon Web Services. The one offered by Amazon Web Services is held up as a good standard example of an SLA. Now, at present, at least at the time of this publishing, if you spin up an instance of a Linux server or something in Amazon Elastic Compute Cloud, and if you read the fine print on their service level agreement, they guarantee a 99.95% uptime. It means if you project that over an entire month, you are guaranteed no more than 22 minutes of total downtime over an entire month. Now, technically, if you read the fine print very carefully, you could have more downtime than that because of the way that Amazon calculates downtime. But for our purposes, this is fine. And you can imagine that a monolithic application, like our Etsy example, is well protected by simply running multiple instances behind a load balancer. It's very unlikely that the same 22 minutes would affect multiple instances at the same time. But if you have 30 interrelated services, and a failure in any one of them would have a systematic failure of some kind, then we are looking at 11 hours of downtime per month, which is half a day. And imagine that that's on your busiest day. And going further, what if we have 100 interrelated services? That could result in as much as 36 hours of downtime per month, which is over a day. Maybe it's your busiest day or your busiest weekend. Now, the example here is somewhat contrived because not all failures would result in a complete outage, and the industry's current way of dealing with many failures would be to simply show an error page when a specific failure occurred on a specific part of the system. But I think that the point is made. We have to take action to isolate failures to prevent cascade failures from resulting in significant outages for large percentages of time. And this leads us to the circuit breaker pattern. Think of a circuit breaker in a house or a car or a boat or anything. What is its purpose? Well, in a house, it ensures that only a certain amount of current can pass through a given circuit. If there is a failure, say by, don't do this at home, but if you were to put a running toaster in a sink full of water, then the breaker would trip and it would open the circuit, and it would prevent any electricity from flowing to that circuit at all. Now, after this happens and you resolve the issue, say by unplugging the toaster, you can manually go over to your breaker box and you can reclose the circuit by flipping the switch on the breaker. The main point of the circuit breaker is to detect a failure condition and to isolate it. It isolates it and it stops it from becoming much worse. In doing so, it prevents a cascade failure. It prevents your house from burning down, basically. Now, with this understanding of a physical circuit breaker established, let's talk about how to implement software-based circuit breakers with Hystrix. So similar in concept to the circuit breakers used in your house, we can use circuit breaker constructs in our software, and that is exactly what Hystrix is. Hystrix is part of the Netflix open source software set of libraries, and as such, it is battle tested and is being used by Netflix in production right now as you watch this. Spring Cloud simply adds a lightweight, easy-to-use wrapper, so Hystrix is as easy to use as adding a dependency and annotations. Now, just like a physical circuit breaker, Hystrix detects failure conditions. Let's say that we are calling a service, and we start to get repeated failures in a brief period of time. Hystrix will respond by opening the circuit, and opening means it's not going to allow further calls to take place. The default behavior in Hystrix is 20 failures over any 5-second window of time, but that's adjustable. I'll show you how later. Now, unlike a physical circuit breaker, we can define what we want to do when the primary service call is not available. In a physical circuit breaker, it just shuts off, but in Hystrix, we can do something else. For example, we may resort to cached values, or we could simply not display something to the user. You can think of this something like a giant catch block. Like we have try, catch, finally blocks in Java. The difference is this doesn't apply to individual calls, but to all calls that would be happening while the target service is unavailable. One interesting thing you can do here is you can have the fallbacks work in a chain. So you can have a primary action. If that doesn't work, you can go to a fallback action. And if that doesn't work, you can go to a third fallback. Now, Hystrix is designed to reclose itself after an interval to see if situations have improved. After all, sometimes in a cloud environment, the failure is just that the given service is simply temporarily overwhelmed with too many requests. By default, Hystrix will reclose the circuit after 5 seconds. Here is a side-by-side comparison between the Hystrix circuit breaker and the physical circuit breaker in your house. First, be sure you have the terminology right. When everything in your house is operating normally, we say that all of the circuit breakers are closed. And when a failure occurs and a breaker trips, we say that the breaker is open. This terminology makes perfect sense if you were to look at an electrical diagram. And the Hystrix circuit breaker uses the same terminology. Closed is good, open is bad, even though it might seem opposite. Physical circuit breakers are designed to protect against one type of failure, excessive current flow. With Hystrix, the definition is more flexible, but we are essentially looking for exceptions or timeouts occurring within a time interval. We're not looking at excessive flow. Presumably that would manifest itself as a slowdown and a timeout. Now, when physical circuit breakers are open, the circuit is completely disabled and that's it. With Hystrix, we have the option of determining a fallback behavior. For example, let's say in our shopping application, we have a recommender service, and at some point it becomes unavailable. We could simply choose to display something else on that portion of the screen in the interim. And finally, if one of the circuit breakers in your house trips, you have to manually get up, diagnose the problem, go to the breaker box, and reclose the breaker. With Hystrix, the resetting is done automatically and is configurable, though a manual option is still available. First, you'll need to add the dependency for Spring Cloud Hystrix. Fortunately, there's a starter for this, so as long as you have the Spring Cloud parent or equivalent dependency management section, you'll be all set. Next, simply switch Hystrix on in one of your configuration classes. At this point in the course, you should certainly be able to see the pattern here. Now here is an example of actual Hystrix use. This is an ordinary Spring bean marked with @component annotation. Of course, any stereotype annotation could be used here, or none at all, as long as it is instantiated as a Spring bean. Next, we have a getStores method as an example. Imagine the logic here is to make an external call and it is subject to failure. So we will mark it with a Hystrix command annotation. In this case, a fallback method is identified. The fallback needs to have a matching signature in terms of parameters and return type. When this code runs, depending on the state of the circuit breaker, one of these two methods will be executed. Hopefully, in normal running, the primary will be executed most of the time. But if we are in a failed state on that remote service, the fallback will be run. Now, if we wanted to make it even more interesting, the default stores method itself could be instantiated with a Hystrix command, and it could indicate a tertiary fallback. And there's really no limit to the number of levels, though I think it would probably be rare to find too many real-world cases with more than 1 or 2 levels. One thing that Hystrix allows us is a good deal of fine-tuning regarding the failure detection and recovery behavior. In this example, we've adjusted the error threshold. This is similar to changing the amperage rating on a physical circuit breaker. In this case, if Hystrix detects a 20% failure rate over a 10-second moving window of time, it will trip the breaker. We also see here that we have determined that a 5-second reset time is too leisurely, so we've set it to a quicker 1-second response instead. If you want to see all of the options that are available, and there are quite a few, take a look at this link to the Hystrix Javanica library. Javanica is Netflix's Java library for Hystrix, and I think their documentation here is really quite good, much better than what they've done in the ribbon documentation, for example. To make it more interesting, the Hystrix command gives us some really nice options for how we want the target logic to be invoked. The default behavior is synchronous execution, the same as we were expecting. We execute the command, and when it's done, we get the control back. In the interim, we are tying up one of our threads. This is exactly the same anytime you call one Java method from another Java method. But, as you can see here, we also have the options to fire the command in a separate thread. This is essentially the same as what I can do with Spring's async annotation, except that we're adding the circuit breaker feature to it as well. This is an excellent way to improve the throughput if I have multiple work items that do not necessarily need to be run in a sequential order. And it is really easy to implement these two because all we need to do is have the method signature return a Java future. Even more interesting is the reactive model. This is asynchronous as well, but even better because we don't need to query a future object to see if it's done. We can have an observable that will be executed, and as soon as the work is done, the responding logic will be fired, and therefore all we have to do is listen to the event. So let's take a look at some examples. Here is an example of asynchronous command execution via Hystrix. Essentially, the only real difference is the return type. Any return type based on a Java future tells Hystrix to invoke the method in a separate thread. The caller of this method gets the future immediately and has the option of checking the future to see if it is done and what the result is. The only unusual part about this is the async result. Suffice it to say that the returned value needs to be wrapped in an async result to keep the compiler happy. The invocation takes place in another thread managed by Hystrix. And here is the reactive model. Notice that the returned value is some kind of observable. This instructs Hystrix to use the reactive model for invocation. The caller of this code will get the observable and can subscribe to it as a listener. The listening code will be invoked automatically as soon as the call is complete. Note that, similar to the previous, the method needs to return an observable result to make the compiler happy. By the way, the classes that you see here, the observable, this is actually the Java RX observable, not the Java Lang observable. As mentioned, there are a number of useful properties that you can set to fine-tune the behavior. This is a short set of helpful ones. A nice one off the bat is related to timeout. Sometimes our systems are sensitive to more than just failure, but also slow performance. We may decide that if a target service's performance degrades beyond a certain point, we might as well consider it unavailable. Besides, perhaps the reason the target service is slow is because it is being overwhelmed with work, and opening the breaker will give it some breathing room. The request volume threshold is actually tricky to understand. This is describing the threshold beyond which we want the circuit breaker logic to be active. This is not talking about the number of errors. When I first saw this, I thought it was the number of errors. What it's saying, for example, is saying that we could say that if we have less than 5 transactions within a 10-second period, we might not want the circuit breaker functionality to even be active, even if all 5 fail. The error threshold percentage is easier to understand. This is simply setting the amperage of our breaker. If more than some percentage of attempts fail within a moving 10-second time window, the breaker should open. Default is 50%. We'll consider 50% to be a systemic failure. Now, I've mentioned a few times about a 10-second period or a 10-second moving time window. This window is configurable using this rolling stats property. Essentially, Hystrix keeps track of the exact time when each failure occurred. When a new failure occurs, it adds it to the collection, throws out any events that happened before the threshold started, and it checks the threshold. The Hystrix circuit breaker is designed to reset itself. After all, if the circuit breakers required manual interaction to reset them like the ones in our houses, then if we had hundreds of them throughout our code base, we would have created a different kind of nightmare. So it's better to describe to Hystrix what our policy is, or what policy we would like it to follow to automatically reset the breakers. The main item to control is how long we would like the circuit breaker to stay open before Hystrix tries to close it again. This is controlled by the sleep window property that you see here. You can also force the circuit breaker open using the forced closed property, but it is a bit difficult to think of a realistic case to use this property. Now at this point you have enough knowledge to work through the exercise at the end of this module. But before we stop, I'd like to introduce you to some interesting monitoring options that you can use to keep an eye on all of the circuits in your system so that you can visually see that everything is running successfully. One thing that is important to consider in any microservice environment is the monitoring of the various services. One of the items we should really keep an eye on is our circuit breakers and how often they are tripping and why. A really nice feature of Hystrix is the Hystrix dashboard. This provides a nice little web interface showing the state of all of the circuit breakers within an application. Now it takes a bit of time to get used to what the display is telling you, but in time you can see that it is giving you a lot of insight into your application. Now if you want to use a Hystrix dashboard, you add the Spring Cloud dependency for the dashboard and make sure that Spring Boot Actuator is also present. To enable the dashboard within your configuration class, in addition to the enable annotation you have for Hystrix, you add the enable Hystrix dashboard. So again, it's not the same annotation, it's not the same dependency. They're both extra. Now when you run your service, accessing the Hystrix dashboard is actually a little bit tricky. The easy part is to simply access the /Hystrix endpoint on your service. You'll see the Hystrix web page that you see here in this screenshot. This is not the actual monitor. What this page is doing is it's actually asking you what you want to monitor. It's prompting you to enter the Hystrix stream to be used to display the actual monitor. Now if you take a close look at the text, and if you temporarily ignore anything related to the word turbine, you can see it is looking for you to enter the URL of a stream. All of the Hystrix enabled services will automatically emit a stream from an endpoint called hystrix.stream. You can enter the URL of any of your services to monitor them. But to monitor this service itself, just copy the URL from your browser up at the top there and paste it down below and add .stream. The delay is how often you want the screen to refresh, and the title is just what you want to display on the top of the page. The main thing is the stream. So just click on the button Monitor Stream. And the next thing you will see is the Hystrix dashboard. This web page is actively monitoring whatever stream you indicated earlier. In fact, you could actually stop the underlying service and it would still keep monitoring. In this example, I've pointed it to the sentence and word service we've been working on in this course, where the methods were annotated with the Hystrix command illustrated a few slides back. Each method annotated with Hystrix command shows up here. For purposes of an example, I deliberately caused a failure so you can see what an open breaker looks like. I made the sentence method fail by simply not starting some of the word services and not providing a fallback. You can see the get word circuit is fine. Of course, it isn't being called in my example here. Now before we wrap up and do the exercise, let me introduce you to Turbine. The Hystrix dashboard I've just shown you is very nice, but if we have a large number of microservices, it isn't really practical to install and visit a dashboard on each one. So the solution is what we call Turbine. Turbine is simply a single Hystrix dashboard that listens to and aggregates the streams of all of the other Hystrix-enabled services. It's fairly easy to set up. You add the dependency and enable Turbine, and it interacts with Eureka to find all of the client services. I won't provide an example here of Turbine, but you can take a look at the Spring Cloud reference to see how to set one up. It's relatively straightforward. So to summarize, software circuit breakers protect against cascade failure. Spring Cloud Netflix Hystrix provides an easy way to add circuit breakers to your applications, just a dependency and annotations. And you can use the Hystrix dashboard and Turbine to monitor your circuit breakers. So now it's time for an exercise. Take a look at Lab 7 and set up some circuit breakers.